Consider a rigid rod of uniform mass on top of a frictionless table. The center of mass, which is located at the center of the rod, is shown here as a black circle. The rod is not moving on the table. This is a situation of static equilibrium. Why is the rod not moving? Well, according to Newton's first law, if the net force acting on an object is zero, then the object will stay at rest. The condition that the sum of the forces equals zero is known as the first condition of equilibrium. This obviously means that the sum of forces in all directions is zero. In the case of the rod, it could move in the x and y direction, so the net forces in the x and y direction must be zero. But in the case of an extended object, this condition may not be enough to ensure that the object is in equilibrium. Let's consider the rod again. Imagine that the forces shown are acting on it. What is the net force in this case? If we calculate the sum of all forces, we get the result shown by the red arrow. So this is clearly not a situation of equilibrium. In order to get a net force equals zero, we need to apply a force that is equal and opposite to the sum of all other forces. This is what we have done here. Now the sum of all forces is zero. However, the rod will still move. Why? Because the forces are applied on different positions, and they are exerting torques on the rod. The sum of all these torques is not zero, and thus we are causing the rod to rotate. We have moved the blue force so that its torque is enough to balance the sum of all other torques. Now the net torque is zero, and the net force is also zero. The rod won't show neither linear nor rotational motion. This is the second condition of equilibrium. The sum of all torques equals zero. So, to summarize, for a body to be in static equilibrium, both the sum of forces and the sum of torques applied to it must be zero.